Welcome to qnawire.
So we can apply conservation of angular momentum to the collision. Now, linear momentum is not conserved because the force that's applied to the rod is at the axis. And since the force is acted on the axis, so there's no torque. So that means there will be, so if there's no torque, then angular momentum must be conserved, but linear momentum won't be conserved. So if we say L1 is the angular momentum before collision and L2 is the angular momentum after collision, so they should be conserved, and in other words, they should be equal. And we're given that the mass of the bullet is 1/4 of the mass of the rod. So that's the bullet that's hitting at the middle, and then both of them are moving together. So let's find out L1 first. So L1 is MBVR because we have the momentum of the bullet times R, which gives us the angular momentum before collision. And if we replace MB by M rod, we know that MB is 1/4 of M rod. So that gives us this quantity right here, where R is half of L because it hits in the middle. So we get 1/8 M rod VL. And L2 is basically I times omega, where I must be equal to the moment of inertia of the rod and the moment of inertia of the bullet. And to do so, we see that the moment of inertia of the rod is 1/3 m rod L squared, and for the bullet it's mb r squared. And again, we replace mb by this relation to get mb in terms of m rod and L. So we add them together to find out L2, which is this quantity right here. So if we set them equal to each other, we have this following relation, and from there we can write the equation in terms of omega, and we see that omega is 6/19 V over L. So once we know omega, we can, that concludes part A, where we had to find the final angular speed of the rod. Now, once we know omega, it should be easy to calculate the kinetic energy of the system after collision and before collision. So before collision, it's just half mv squared, where m is actually mass of the bullet, so that's going to be mb, and we can replace mb by 1/4 of m rod, and then this is the kinetic energy before collision. And after collision, since the system rotates, so we'll have I omega squared times half, and again I is the moment of inertia of rod plus moment of inertia of the bullet, which we calculated earlier in the previous section. So we can write that, and also we found out the relation between omega and v, which we can use here as well. And that gives us K2 as 3/152 m rod v squared. Now it's just a simple ratio that you need to take. So we're going to find K2 over K1 from this expression. And we see that if we do so, the ratio becomes 3/19. So that's the ratio of the kinetic energies after collision to before collision. Thank you.